Welcome students. Today we are going to start to discuss two very important concepts called controllability and observability. So these are the two notions which are the core concept of state space realization, and you will find that these two concepts will be very much useful to design the controller as well as observer in state space. So one by one we will discuss. So this will be the outline of presentation. Now first about the controllability. So the what is the motivation to understand the concept of controllability? So a basic question has been asked, that can we correct the course of satellite in space, that is bring it from the wrong coordinate to the desired coordinate? Means suppose in space the satellite having a particular position. Okay, so with the control input, now the question has been asked that with the control input, if we want to change the coordinate of the satellite or the position of the, in simple sense you just think that if we want to change the position of the satellite, the with the control input in finite time, is it possible? That has been asked. The similar question has been asked, that can we treat a sick person so that he is transformed from a sick state to a healthy state? Means suppose a person is sick, and with the help of drug, can we transform the sick person to a sick state of the person to a healthy state? Okay, so the similar question can be asked for the state space realization. How? Now suppose we have a realization of LTI system is x dot equal to a into xt plus b into ut, and yt equal to c into xt, and the initial conditions are x0. So now the question is similar question what we have asked here. The similar question we can ask, that can we move xt to an arbitrary xtf, means t to tf, means xt to a, means can we move xt to an arbitrary xtf from x0 in the state space using an appropriate ut in finite time? Okay, that try to understand in finite time. Means here the finite time is important for these two cases also. Suppose a sick person, if the sick person will recover, it will take, or he or she will take time to recover. For infinite time it is meaningless. So here the same thing for the system also. So suppose if we are at a position x0 at initial at any initial state x0, so can we go from x0 to any arbitrary state xtf with the appropriate choice of ut, means the control input ut in finite time? So if an input to a system can be found that takes every state variable from a desired initial state to the desired final state, the system is said to be controllable. Otherwise the system is uncontrollable. So this is the basic concept of controllability. Means is there any control input exist such that in finite time is finite time we can transform we can transfer any initial state x0 to the arbitrary final state xtf. Okay, and if the answer is yes, if it is possible for every state of a system, then we will say that system is completely controllable. If any of the state is, if we'll see that it is not we are not able to move with the influence of the control, then it is not possible. So sometimes this concept of controllability is also known as state transfer problem, because whether we can transfer the state from initial to the final or not, that is the question. The answer will be given by the test of controllability. Okay, now controllability by inspection. So when the system matrix is diagonal, and as it is for parallel form, it is apparent whether or not the system is controllable. Means if the system is represented in diagonal form, that already we have understood that if a system is given, how we can transform the system in diagonal, and that is one of the advantage. If the system is represented in diagonal form, then by inspection actually we can comment about the controllability of a system. Means whether we can say that whether the system is controllable or not. Okay, suppose one signal flow graph of a system has been given. Okay, this is 1 by a, so here it is a third order system because three integrators are there, and it is in a diagonal representation, because if we want to write the state equation, then we can write that, you see, it is x1 dot will be minus a1 x1 plus u. Okay, and similarly x2 dot will be minus a2 into x2 plus u, and x3 dot is equal to minus a3 into x3 plus u, and which is written in the state space representation. Okay, so x1 dot is also, here it is in a diagonal form. The minus a1, minus a2, minus a3 are the diagonal elements, and we can write the state equation also. And here again I want to mention that, you see that the form in the diagonal, the advantage is that all the dynamics are decoupled. Means x1 dot only depends on x1, x2 dot only depends on x2, and x3 dot only depends on x3. Now the question is that, can we transform the state x1, x2 and x3 from their initial state to any of the final state with the influence of u? The answer will be given from the solution. So now for every state x1, x2 and x3, we can write the solution in this form. Okay, so we are finding that xit equal to e to the power ait xi0 0 to t e to the power minus ait minus tau biu tau d tau, and you see each of the equation is independent and decoupled from the rest. The control u, you see from here also it is very much clear. The control u affecting the each of the state variables. This is the controllability from another perspective. Means if the u, you will find that is present, which is influencing the state x1, x2 and x3 respectively, then it is possible to transfer from any initial state x10 to x1tf, x20 to x2tf, x30 to x3tf. Okay, but if you see in contrast to that another structure where you are finding that this is not connected. Okay, this u is not connected to the state x1, and if we write similar to the state space equation, you will find that here this element is 0, and similarly x1 dot equal to minus a4 x1, x2 dot equal to minus a5 x2 plus u, x3 dot equal to minus a6 x3 plus u. And from here it is very much clear that it is possible to influence the state x2 by u, it is possible to influence the state x3 by u, but it is not possible to influence the x1 by the control input u. So that's why the whole system is uncontrollable. If, as I told you, that if any one of the state is if we found that it is not possible to transfer the state from any initial state to the final state with the influence of u, then the whole system will be uncontrollable. And you can find from the solution also that x1t, you see this element is bi element is 0, so there will be no control input by which you can influence the x1t. So we see that the state variable x1 is not controllable by the control u, thus the system is said to be uncontrollable. Okay, in summary, a system with distinct eigenvalues and a diagonal system matrix is controllable if the input coupling matrix, means B matrix, does not have any rows that are 0. So if you found that for the first structure, if all the elements are 1, then, and mind that the condition is that the system should have distinct eigenvalues. Along with that, the system will be in a diagonal canonical form, then only you can check the B matrix whether all the elements are 1 or not. Okay, it is not possible to comment about the controllability by inspection if it is represented in any other form. Okay, so that's why the next topic is that if the system in general it is represented, how can I test the controllability of a system? So that's why the definition of the controllability is, again, it is stated that if I have a system x dot equal to a into xt plus b into ut, but here we have taken a system which is multi-input, that is u belongs to rm. It means that m number of inputs are there. Okay, is said to be completely controllable if given any initial and final state x0 and xf, there exists some tf, finite time tf, greater than 0 and continuous input ut, such that xt0, if it is x0, we can obtain from there xtf equal to xf, means we can transform the state from x0 to xf. And the main result, what you have to remember, that system is controllable if and only if the controllability matrix C equal to B, AB, A square B, A to the power n minus B belongs to Rn cross Nm, means the dimension. Why the dimension of this matrix will be n into n cross Nm? Because as I told you that we have m number of inputs. If the m number of inputs you have, if the m number of input you have, then what will be the b dimension of b? So x dot equal to ax plus bu. Okay, now we are telling that it is m cross 1, so obviously it will be n cross m, b will be. So now the controllability matrix has been formed by b, so it will be n cross m, AB, so it will be n cross m, and also the A is n cross n, so ultimately it will be n cross m, and we are going up to a to the power n minus 1 into b. Okay, so it is also will be n cross m. So these all column vectors, if you stack and to form the and if you form the controllability matrix, then its dimension will be n into n bar n cross m. But if you are dealing with a CISO system, for that case m will be equal to 1, then the dimension of the controllability matrix means b, ab, and then a to the power n minus 1 into b will be a square matrix, that is n cross n. Okay, so that's why it is has been tell if the controllability matrix C has rank n, if you able to prove that the controllability matrix after forming that it having rank n, then the system is completely controllable. Okay, for a CISO system, m will be equal to 1. At that case, controllability matrix will be C belongs to R n cross n. Okay, so now many of you are thinking that how this controllability matrix has been formed. Okay, so B, A, B, A square B, A. So for your exam, I can say you that you have to remember this main result exam, as well as for the many competitive exam like GATE. I have seen that the questions are coming from here, so that's why this concept you have to remember. And then this portion will help you to understand that how this controllability matrix we will get. Just a rough sketch I am going to give you, not the entire proof. Okay, and one thing you remember that it is so it is a state transfer problem, means whether we can transform any initial state to the final state with the existence of the with the continuous input ut or not. So that's why it is related with the state equation only, so output is not coming into picture. Okay, so it is a relation of ut and xt, so that's why we are dealing with the state equation only, and to form the controllability matrix only A and B are involved, the C matrix is not involved. So controllability concept is dealing with the input as well as input and state, so that's why A and B matrix are involved. Okay, now how the C matrix has been formed. So now a CISO system we have taken, LTI system x dot equal to axt plus but. Okay. Now if we want to transfer the state from any initial state x0 is equal to 0, means from the origin to any final state xft, then the solution can be written 0 to, because that e to the power at x0 part will be 0. Due to that, we have assumed that we want to transfer for the state for the system from origin to any other state except. So solution we can write 0 to 2 e to the power at minus tau b of u tau d tau. Now we will change the variable, that t minus tau we have assumed tau 2. So from here we can write d tau equal to minus d tau 2. Okay, so from here we can write except t equal to 0 to t e to the power a tau b of t minus tau d tau. Okay, d tau 2. So now from the Cayley-Hamilton theorem we know that e to the power at, means e to the power at will can be written I equal to 0 to n minus 1 ai alpha it for some computable scalar alpha it, that already we have discussed when we have discussed how to compute the e to the power at using Cayley-Hamilton theorem. Okay, so now similarly x of t, we will substitute e to the power at in the equation number 3 and we are getting like this, and which can be written that I equal to 0 to 1 summation a I b b I t. Okay, so how actually this equation will look like? So now x of t you can, and what is your bit, for coefficient bit, that depends on the input u. Okay, and now most interestingly that how this xft is now. So the result can be interpreted as the xft is a linear combination of n vectors aib. Okay, so how it will be? Now it will be something like this, that you have written that xft, the final state is summation of I equal to 0 to n minus 1 a I b, okay, beta I of t. Okay, now if you just expand, so it will be b beta 0 t plus a b beta 1 t. So like that the terms will be there, a to the power n minus 1 b beta 2 t. So that's why it has been written that except t, the final solution is a linear combinations of the that n number of vectors, that is b a b a. So now this can be written, that is b a b a n minus 1 into b into beta 0 t like beta n minus 1 into t. Okay, here it will be n minus 1. Okay, so now you carefully observe. So this is the xft. So when this solution will exist, okay, when this xft, the solution, unique solution will exist. So now the solution, so this is your controllability matrix. So this controllability matrix into this, the coefficient, okay, that is beta 0 to beta n minus 1. Okay, so this is the x of t. Now it is very much clear that the solution will exist only when this C matrix having full rank. Okay, so that's why here we will conclude that any vector x of t can be represented as a linear combination of these n independent column vectors b a b a to the power n minus b if the rank of this matrix will be n. So the matrix C is defined as the controllability matrix. So once again I'm telling here the main result you have to remember. If we have a system x dot equal to xt plus b into ut, then we have to form the controllability matrix and we have to test the rank of the controllability matrix. If it is a nth order system, then the rank of the controllability matrix will be n, and then only the system will be controllable. And what is the concept of controllability? It is telling about whether is it possible to transfer all the state of the system from the initial state to the final state in a finite time with a continuous input ut. Okay, so if it is yes, then the system is controllable. Now we will come to some example. So now you say, so in suppose a system is given to you that investigate the controllability A and B matrix has been given, and C matrix has been formed B A B, and it is observed that the rank of the controllability matrix is 2. You can find out the determinant, and if the determinant is non-zero, then we can say that rank of the matrix is 2, then AB pair is controllable. Okay, now then again another example has been given where it is in a controller canonical form A and B, and we have constituted the C matrix, controllability matrix, and we have found that the rank of this matrix is 3 because determinant is not equal to 0, and MATLAB command is there, and after declaring the A B matrix, if you use CTRB A comma B, then it will give you the controllability matrix, and if you check rank of C, then MATLAB will give you the rank of C. If it is definitely for this case, you will get 3. Okay, and another example has been given. You see, it is in a diagonal form. Okay, the controllability matrix will be in the form of this B A B A square B, and here it is very interesting to know that if Bi is 0, any of the element is 0, then this matrix will lose its rank. Okay, suppose B1 is 0, then this entire row will be 0. So if this entire row will be 0, then you will find that it is losing its rank. And also if alpha I equal to alpha j, any of the two eigenvalues are same, then also it can be shown that then the controllability matrix is losing its rank. Okay, so now we will discuss about the controllability is invariant under similarity transformation. Because suppose we have a system, original system x dot equal to ax plus bu and y equal to cx, and with the transformation matrix we have transformed the system in this form: x bar dot equal to a bar x bar plus b bar u, y equal to c bar x bar. Now the question is, suppose this system, the original system, was controllable. So after transformation, whether the system will be still controllable? The answer is yes, because controllability is invariant under similarity transformation, and it has been proved here that claim is controllability does not change. Proof is what? For k equal to 0 1, it can be shown that a bar k b bar, where a bar is written t inverse at to the power k, here it will be t inverse into b. Then if we expand it from the induction, we can write t inverse a to the power k t into t inverse into b, and it is equivalent t inverse a to the power k into b, because t inverse in the is identity. Okay, so now with this property we will prove that even if you transform a system using similarity transformation, if the original system was controllable, the transform system also will be controllable. Okay, so the controllability of the transform system, a bar b bar will be b bar a bar b bar b bar a bar in minus 1 b bar. Okay, and b bar we can write from the relation t inverse b. Similarly for the a inverse b inverse we have written, and from here we from using this property we can write it is actually t inverse of b a b a to the power a n minus b, means t inverse of c a comma b. It means that since the determinant t not equal to 0 means it is always full rank, then determinant of c a bar b bar means the control, if it is not equal to 0 only when determinant of c a comma b is not equal to 0. Thus the new system is controllable if the old one is controllable. Okay, so now we will discuss about the observability. Okay, so what is the motivation to discuss about the observability? Now, the uncontrollability can be viewed best with the diagonalized system, that already with the example we have seen. The signal flow graph showed clearly that the uncontrollable state variable was not connected to the control signal of the system. And why we will study the controllability of a system? Now, the ability to control all the state variable is a requirement for the design of a controller. Means when the next step, when we are going to design the controller, at that time you will find that it is required to test whether the system is controllable or not. If it is controllable, then only the design of controller is possible for the system. Okay, so similar concept governs our ability to create a design for an observer. Means if we want to design an observer, then similarly we have to test whether the system is observable or not. And what is the concept of observability? Now we are using the output of a system to deduce the state variable. Means in simple sense, from the output can we construct all the states of the systems or not. If any state variable has no effect upon the output, that we cannot evaluate this state variable by observing the output. Means if we found that from the output any of the state variables are not possible to reconstruct, okay, then we will say that system is unobservable. The ability to observe the state variable from the output is best seen from the diagonalized system. Okay, so now again we have taken two examples. Here you see it is a diagonalized system, and for the first case this output is connected with all the state variable. It means that from the output we can construct x1, we can construct x2, we can construct x3. But for this case you see the x1 is not connected with the output y. It means that the output x1 cannot be constructed by looking the output y only. Okay, so this representation of the system is unobservable. Okay, so here again it has been described whatever I said, that if the initial state vector x of t0 can be found from ut and yt measured over a finite interval of time t0, the system is said to be observable, otherwise system is said to be unobservable. Means here actually two things are important, that whether the system states can be deduced from the output yt or not. For that the knowledge of input is also important. Okay, so that's why it has been written that, simply stated, observability is the ability to deduce the state variable from the knowledge of input ut and the output yt. So that's why for the configuration A, the output matrix you will find that 1 1 1. It means that, and it has to be in diagonal form. Remember that when all the elements of C matrix is 1 1 1, at that time the system is in diagonal representation, and then only you can comment about that all the states can be constructed by the output yt with the help of ut. Okay, but in the B configuration B, you are finding that one of the element x1 element is 0, one of the element of C matrix is 0, means x1 cannot be constructed by the output y and the input ut. So system is unobservable. Notice that the first column is 0 for system represented in parallel form, means in diagonal form with distinct eigenvalues. If any column of the output coupling matrix is 0, the diagonal system is not observable. So that is one of the advantage, that to diagonalize any system, because once we will diagonalize, it is very much clear that whether which state is observable or which state is unobservable. For controllability also, which state is controllable and which state is uncontrollable, you can see it very clearly. Okay, so now how we will test the observability of a given system. Now suppose if you have a MIMO system where input belongs to RM and Y is a P number of outputs are there, is completely observable if given the input and output signal UT and YT for T belongs to 0 to T, means in finite time, from 0 to T finite time, we can always reconstruct exactly the initial state x0. Then only we will say that the realization is observable, and we can construct the observability matrix like this: C, CA, CA n minus 1, which is below, whose dimension in NP by N, and if you have a single output means P equal to 1, then this matrix will be N by N. Okay, so this matrix is known as observability matrix, and if the system is observable, then this O matrix means observability matrix should have the full rank, that is N. Okay, if we are dealing with second order system, then observability matrix, if we find that it is rank 2, then we will say that system is observable. Okay, so similarly here we will discuss that how the observability matrix O is formed. Okay, this O matrix, how it has been formed, just a basic idea I am giving. Suppose we have already in the beginning of the class we have discussed, if a nth order differential equation is given, how this nth order differential equation can be implemented using operational amplifier or the analog computer in the laboratory. Okay, we require n number of integrator, and output of the integrator will be the states. Okay, that is x1, x2, xn, and by giving the name of the output of the integrator x1, x2, xn, this original nth order differential equation can be converted in number of first order equation, which is represented by sorry, a matrix notation, that is x dot equal to ax plus bu, y equal to cx. Now after getting this system, suppose the system is now represented by n number of first order equation, can we just actually start to simulate, means can we solve this system immediately? The answer is no, because if we want to start the simulation, or if we want to solve the system, then we require the knowledge of x10, x20, xn0. But for the original system, only we know the y0, y dot of 0, yn minus 1 of 0. Okay, so now the question is that how do we determine the initial condition x10, x20, xn0 of the integrators from the given initial condition of the differential equation y0, y dot of 0, y of n minus 1, 0. So to understand that, for the simplicity, we will assume that suppose u is 0, input time being is 0. So now we have the state equation only x dot equal to ax, y equal to cx. Okay, so now how can I give the answer? Now that can be given the answer that suppose y equal to cx, we will differentiate y once again. So c into x dot. So now x dot equal to ax plus bu, but we have assumed u is 0, so it will be cax. Similarly, y double dot, we can write c square. So like that, if you differentiate up to n minus 1, we are getting ca n minus 1 into x. Okay, and now if we want to write in a matrix notation, then that capital YT, we can write yt, y dot t, y of n minus t, the dimension is n by 1, and then c square, c n minus 1, its dimension will be n cross 1, and then we have the xt. So final relation we are getting yt equal to o into xt. Now what was our question? Question was that given y0, y dot of 0, can we find x0? Okay, so this relation will give you the answer. This is the direct relationship between the given initial condition of the differential equation, that is y of capital Y of 0 minus, and that of the integrator of the implementer, that is x of 0 minus. So then x of 0 minus can be found out that observability matrix inverse into y of 0 minus. So now you are finding that the solution, the unique solution exists only when this observability matrix is invertible, or it having full rank. So that's why the observability matrix has been formed like this. Now one can argue here that why we will differentiate the output up to n minus 1, means why this matrix has been formed up to a n minus 1. The answer is that from the Cayley-Hamilton theorem, it can be shown that even if after that if you add C A n C A n plus 1, these rows, if you add, the rank of this O matrix is not going to be changed. That rows will be redundant. Okay, that can be shown. So but that is not required time being. You can, if you can remember the final result of the observability, that is more than enough. Okay, so now we will solve an example, and example is like this, that suppose we have a system x dot equal to suppose a system is represented in a SFG, and it has been asked that compute whether the system is observable or not. So don't be misled by the diagram. You see, if you see the diagram, x1 is not connected y with the y, you can think that the system is not observable because this x1 is not be constructed by the output y. But remember that this philosophy is only, or this argument is only valid for the system which is represented in diagonal form. But here the system is not in a diagonal form, it is in a controller canonical form. Okay, so x dot equal to ax plus bu y equal to cx. So to test the controllability, what we will do, we will form the observability matrix C C A C A square, and we will find out the determinant. We are finding the determinant is minus 344. So OM is full rank to 3. The system is thus observable. So you might have been misled and concluded by inspection that the system is unobservable because the state x1 is not fed directly to the output. Remember that conclusion about observability by inspection are valid only for the diagonalized system that have distinct eigenvalues. Okay, and another fact here I want to tell you that similar way, if a original system is observable and if you transform it, and the transform system also will be observable, like controllability what we have seen. So now another thing here I'm going to discuss today, that is controllability and observability duality. Okay, suppose a system we have taken x dot equal to ax, y equal to cx. Okay, another system we have built. How? Now taking A matrix is the A transpose and its B matrix is the C transpose. Okay, now it has been claimed that if this system is observable, if and only if this system is controllable. Okay, how the proof has been given? Now the controllability of this system can be written controllability A transpose comma C transpose, because it is its A matrix and this matrix is its B matrix. Okay, so we know that B A B A n minus 1 into B. So here B is C transpose, so C transpose, then A transpose C transpose, then A transpose n minus 1 C transpose. Now this can be written C C A C n minus 1 whole transpose, and you see C C A C n minus 1 is basically the observability matrix of AC, and we can write observability A comma C transpose. Now if observability matrix is non-singular, if and only if the controllability matrix is. So if this system is controllable, then definitely this system will be observable, or vice versa. If this system is observable, this system will be controllable. So this is the controllability observability duality. In right time we will use this theorem. Okay, so we will recollect this concept when it is required. Okay, so today I will conclude very important thing, that is controllability and observability, how it is affected by pole zero cancellation. That is very important to know. Okay, suppose we that's why we have taken a very simple system, scalar system, that is 6 by s plus 2. Okay, so here we will go back to the board, and we have taken ys, okay, by us is equal to 6 by s plus 2. Okay, and now If it is like that, then we can write y dot plus 2y is equal to 6u in time domain. Okay, now you see we have taken for the model development, state space model development, we have taken y equal to 3x1. okay, it has been defined like this. We have taken y equal to 3x1. okay, fine, sorry, 3x1. okay, now if I want to find out the state space model, how we can find out? We can do like this, that is what is your y dot, then if we substitute this here, that is it is 3x1 dot, okay, plus 6x1 is equal to 6 into u, okay, which we are finding that can be written x1 dot plus 2 into x1 is equal to 2 into u. okay, and the state equation then we will get, it is a scalar equation, so 2x1 plus 2 into u. So this is the state equation. okay, so this is your model 1. it has been given model 1. okay, now what we did, we are building another model, that is model 2, but we have considered, we have augmented another state with this state equation. okay, with this state equation, so model 2 we are building, model 2 we are building. In model 2 what we have done, we have taken the first equation, okay, but along with that we have added another, we have taken another equation, x2 dot is equal to, suppose it is something what we have taken, that is minus 1 into x2 minus 1 into x2 plus 1 into u. okay, 1 into u. So and we have represented it by the state equation once again, and we have kept the output same, that is for this system also, for this system also output we have taken 3x1. so we have represented this model 2 using this state space equation. okay, now we are computing the and you observe that this model 2 is clearly different from the model 1. okay, and it is bigger also. You see, it is a first order equation, it is a second order equation. okay, because it is its dimension, its A matrix is 1 by 1, but here A matrix is 2 by 2. It is different, it is bigger, larger. So now for this system we are computing the transfer function g bar of s. So it is 3 0, then si minus a inverse into b. okay, so now if you consider it, you are finding that you are getting 6 by s plus 2. You see, we got for this model the transfer function is 6 by s plus 2. For this bigger model also the transfer function is same. So now we have two very different model that results in the same transfer function. okay, why it has happened, what is going on? Now why it has happened, now you look very carefully, this system is in a diagonal form. okay, and in the diagonal form this C matrix, one of the element is 0. okay, the x2 element is 0, and if the x2 element is 0, particularly this mode, that s equal to minus 1, means this eigenvalue is not, or you can say that this particular state is not observable. This x2 state, what the state we have augmented, this state is not observable from the output. okay, so and this has happened, why the transfer function is same, because this has happened due to the pole zero cancellation, that s plus 1 and s plus 1 is not visible. okay, so for the system we say that the dynamics associated with the second state are unobservable, which using this particular sensor, okay, which defines by the structure of the C matrix, there could be a lot of motion associated with the x2, but we would be unaware of its using this sensor. Means the due to this construction of the C matrix, okay, what will happen, even if there will be a lot of variation in the x2, that cannot be captured by the output with the help of input ut. So that's why this system we will say will be unobservable. The system what we have built here, this system is unobservable, though the transfer function for this system and this system is same. And this has happened due to the pole zero cancellation. Also you are finding that this mode, particularly the s plus 1, is not visible in the transfer function. So similar analogous problem can happen in the input side also. Means we have a same scalar system, and now we have added a second dynamics in such a way that it is simply x1 equal to minus x2. Okay, and your y matrix is 3 and 2. Okay, so now what will happen, you are finding that this particular for this particular system, if we found out the transfer function, still its transfer function is same 6 by s plus 2. And why it has happened? Because this particular x2 dynamics is not controllable with the control u. So once again the dynamics associated with the pole s equal to minus 1 are cancelled out of the transfer function, but in this case it occurred because there is a 0 in the B matrix. So in this case we can see the x2. You see here x2 is visible, but the due to the construction of the C matrix, but we cannot influence the state with the input because B matrix is 2 0. So now this system is uncontrollable. Okay, and thing can be more worse, because you see, if we take a model where B matrix is 2 0 and Y matrix is 3 0, then what will happen? The particular x2 dynamics will be not controllable as well as not observable, but in that still you will find that transfer function will be 6 by s plus 2. So get some result, same result for the transfer function, but now the dynamics associated x2 are both unobservable and uncontrollable. What is the summary? Summary is that dynamics in the state space model that are uncontrollable, unobservable, or both do not show up in the transfer function would like to develop model that have dynamics that are both controllable and observable, called minimum realization. Means if actually after pole zero cancellation, if you have a system realization and if you find out the controllability and observability, and if you see that it is both controllable and observable, then we will say that system is, the realization is minimal realization. Means this can happen, means the same system can be controllable, can be it's the same system. What we want to mean that the same system means with the transfer function you are finding the same system, same transfer function, but it can be unobservable, it can be it can be controllable, but it can be unobservable, it can be uncontrollable, but it can be observable. Okay, so anything can happen if there is a pole zero cancellation. So you must be careful when there is a pole zero cancellation. Okay, so if maybe the system look like same with respect to the transfer function, but realization in state space will give you the different result. Okay, so here I will stop. So today here I'll stop by drawing the conclusion. What is the conclusion? Today we have understood the definition of the controllability, a concept of the controllability, and then we have understood how the controllability matrix can be formed, and we have understood that if the controllability matrix having full rank, then only the system is controllable. Then we have understood about the observability, and then we have seen that how the observability matrix can be formed, and a system is observable only when the observability matrix having full rank. Okay, then we have understood the very two important thing, that our controllability and observability are invariant after under similarity transformation. And then we have understood that controllability observability duality theorem, and at last we have seen that what are the effects of pole zero cancellation in controllability and observability. Okay, thank you.